Okay, we're continuing our exploration of distinct linear factors. Still talking about the method of partial fraction decomposition. And here we're going to finally see a full example where we have a basic quadratic denominator that we're going to factor into two linear factors. So the denominator here is x squared minus 4, which factors into x minus 2 times x plus 2. So we seek a capital A and a capital B such that this rational function will split into a over x minus 2 plus b over x plus 2. And this works because we have two distinct linear factors, and so the method indicates that we can write this as a sum of those two rational functions, with the numerators now being just real numbers. So what we can do here is we're going to convert this again to a polynomial equation by multiplying by the least common denominator, x squared minus 4. So this will turn into x minus 1 equals a times x plus 2 plus b times x minus 2. Now, in this method, we're going to use, once we convert this into a system of linear equations, we're going to use the elimination method from Math 120. So let's go ahead and multiply this out. So we get ax plus 2a plus bx minus 2b equals x minus 1. And by collecting x terms and constant terms, we get x equals ax plus bx equals -1, and -1 equals 2a minus 2b, which simplifies even further to just 1 equals a plus b, and -1 equals 2a minus 2b. So if we use the elimination method, we're going to try to get rid of one of the variables here by multiplying one of the equations on both sides by some constant number that will allow us to then combine both of these. So what I'm going to do is going to take my first equation, multiply it by 2. So 2, I'm going to call this row 1 for reasons that will be clear later. And that's going to give me 2 equals 2a plus 2b. One common thread here when we're doing, when we're working with more sophisticated math techniques, there are going to be cases where we're going to deliberately make something more complicated so that we can then later on use a method that we know how to use. So right now it seems like, okay, well, we're just multiplying by 2 because reasons, but I promise that there's a reason here. So once we have our new equation and the previous equation, and the other equation together on the same line, now we're going to see how we can add both of these equations, and we'll get 1 equals 4a, and the 2b terms go away. So we just end up with 1 equals 4a, and this indicates that a equals 1/4. And if 1 equals a plus b, then that means b is 3/4. If you're not comfortable following that logic, with skipping those steps, then you're welcome to go ahead and plug that into either one of the original equations that we have. All right, so that's using elimination. And now we have the a and b that we need, and we can simplify the integrand. So the integrand, which was originally x minus 1 over x squared minus 4 dx, is now the integral of 1/4 over x minus 2 dx plus the integral of 3/4 over x plus 2 dx. Pulling out the constant terms here, we have 1/4, the integral of 1 over x minus 2 dx plus 3/4 times the integral of, well, I guess I could just put dx in the numerator there, but I'm just going to go ahead and keep writing it this way so we can see that we just have 1 over some linear factor of x plus 2 dx. And we can carry out the u substitution if we want, but we can whoosh away that detail right now, given that there's a 1 in front of the x, and so if we perform the u substitution, it should just give us du equals dx. And finally, we end up with 1/4 natural log of x minus 2 plus 3/4 ln of x plus 2, parentheses, plus c, and that's the integral. So as you can see, when we are able to rewrite the integrand into these more manageable rational functions, then we can integrate it much more easily. So there really is quite a bit of benefit here. Okay, so now that we have this, we can go ahead and see some more examples. So we're still continuing with the theme of distinct linear factors, so let's not lose sight of that. In our example here, we're going to need to perform polynomial division first, okay? So we're going to evaluate the integral from -1 to 0 of x cubed minus 4x plus 1 all over x squared minus 3x plus 2 dx. Okay, in this case, we can clearly see that the degree of the numerator being 3 is greater than the degree of the denominator being 2. So we need to perform the polynomial division first. Okay, so in case you're rusty, we'll go through it slowly. But I do recommend that you go and review this on your own if you're really uncomfortable. Otherwise, you're going to see me doing the steps and you'll be like, I kind of get it, I kind of follow, but not really. So just like with division of whole numbers, it's the numerator that goes inside the box. So we're going to have x cubed and any missing terms in that polynomial. In other words, we have a cubic term, but we are missing a quadratic term. We're going to need to put plus x squared, plus 0x squared, and then the rest of the terms that we have in the polynomial. So that is our numerator that is going to be divided by the denominator, which is our divisor. So we're dividing by x squared minus 3x plus 2. Okay. And so where we go is we look for the smallest power of x, or multiple of x, that we need to multiply the leading term by in order to get x cubed. So to clarify, what do we need to multiply x squared by to get x cubed? And that term, depending on the order of that term, so in this case it's x, that's going to go in the above the linear term, okay? And it's important to keep track of things like that because then that'll tell us when we're done. So now we're going to go ahead and multiply x by x squared minus 3x plus 2, so the divisor. And that gives us x cubed minus 3x squared plus 2x. So line them up carefully, because then we're going to subtract. We're going to take the difference. X cubed minus x cubed is 0, so we're going to leave that alone. 0x squared plus 3x squared gives us 3x squared. And then minus 4x minus 2x is going to give us negative 6x. And then you can carry down that plus 1 now that we are going to figure out what next we need to multiply by. So x squared needs a plus 3 in order to make 3x squared. So now we're going to do that too. So multiply 3 by the divisor, 3x squared minus 9x plus 6, subtract. And the remainder then is going to be literally the remainder. So 3x squared minus 3x squared leaves us with nothing. Negative 6x plus 9x gives us 3x. And then 1 minus 6 gives us minus 5. Okay, so this is the remainder here. What this means is we can write this as x plus 3 plus the remainder, 3x minus 5, divided by the original divisor. So in other words, we have literally written the original rational function as now a polynomial plus some proper rational function, where the degree of the numerator is smaller than the degree of the denominator. So all of that is to say that now our task fundamentally is to break down this. Okay, the x plus 3 is going to come back. We're not going to forget about that. But let's actually break down this fraction, and we're going to use the method of partial fractions. So first things first, we should factor the denominator to see what the form of the partial fraction decomposition should be. Namely, because it's x minus 2 times x minus 1, we're going to do x minus 2 under A and x minus 1 under B. So if we solve that for A and B, then we should be able to figure out how to get this simpler decomposition. So we get 3x minus 5 equals A times x minus 1, because if we multiply both sides by the least common denominator, then we'll get some nice cancellation like that. And here's a different technique that we can use, okay? This technique will help us eliminate terms and quickly solve, okay? So our undetermined A and B, okay, are solutions to this equation regardless of what x is. And so we can choose x carefully. That'll make one of the terms go away. So notice here that if we let x equal 1, that'll make that go away. And if we let x equals 2, that'll make that go away. And even though in the original problem it's not valid for those values, literally it's not in the domain, the equation will still be true at these numbers. So, and that's for reasons of continuity and whatnot. We won't get into the details of that, but just know that it seems like sorcery, but it works. So we get basically, in 2 steps, we'll be able to figure out what A and B are by plugging in separately x equals 1 and x equals 2. So first, let's let x equals 1. So if we plug that in, we get 3 minus 5 equals, and remember that the first term will go away, because if you plug in 1, you get 0. But the second term, b, is multiplied by 1 minus 2, which gives us negative 1. So negative b equals negative 2. That leaves us with b equals 2. The second one, if we plug in 2 instead, remember that's 3x minus 5, so that's going to be 6 minus 5 equals, in this case, a times 2 minus 1. then we get 1 equals a equals 1. Well, that's nice. So in like 2 short steps, we figured out what a and b were. Okay, putting it all together, this means our integral, the integral from -1 to 0 of x cubed minus 4x plus 1 all over x squared minus 3x plus 2 dx became the integral from -1 to 0 of, and remember, we need the first part of the polynomial division, so the x plus 3 comes first, plus 3x plus 5, minus 5, sorry, over the denominator, which was actually x minus 2, x minus 1, dx. Okay, so this is what we got after performing the polynomial division. Next, by performing the partial fraction decomposition, we have x plus 3 plus, and now we're going to split it up into the 2 terms here. So a, which is 1 over x minus 2, plus 2 over x minus 1 dx. So that is actually what we're going to split. So that polynomial division turns it completely into something very manageable. 4 distinct terms, but they're not bad. And we know how to integrate those. Namely, we have x becomes x squared over 2. 3 becomes 3x. 1 over x minus 2 becomes ln of x minus 2 in absolute value bars. And 2 over x minus 1 becomes 2 ln of absolute value of x minus 1. And we evaluate that from -1 to 0. Okay. Not too bad, right? And then so here, from here, right, we just plug in, right? So we're going to do 0 plus 0 plus ln of -2 absolute value bars, so ln of 2, plus 2 of ln of 1, which is 0. So that's going to be that whole first set of terms, minus, plug in -1, you get 1/2, minus 3, ln of 3, because -1 minus 2 becomes -3, absolute value bar of that, 3. And then lastly, plus 2 ln of 2, because -1 minus 1 is -2, absolute value of that is 2. There we go. All right. And then combine like terms wherever you see them. So -1/2 plus 3 becomes 5/2. Minus, or we'll do ln of 2's first. So 1 ln of 2 minus 2 ln of 2 becomes -ln of 2. So minus ln of 2. And then lastly, minus ln of 3. And that's our answer. So not horrible. Okay. Okay, so then in the next video, we're going to move on to some more exciting ideas, such as when we have repeated linear factors. This gets complicated just the tiniest bit more. And it does mean it's going to involve some more work, and we're going to develop some more sophisticated tools.